Okay, in this video I'm going to give some examples of using the rules of algebra for Boolean functions that involve the basic Boolean functions and, or, XOR, and not. Actually, this table doesn't contain rules for the XOR function, just and, or, and not. Okay. I've already gone over the associative and distributive rules in separate videos. And in one of the more recent videos, I even proved the distributive law using truth tables. Okay, there's some of the others, and I've also done a video just on De Morgan's laws, which allow you to turn ands into ors, or to turn an or into an and. Okay, I've also discussed the double negative. Okay, there's some other rules here that are kind of funny, but they make sense when you think about them, and I'll go through them right now. So, for example, if we have a statement that says P and P, that's equivalent to just saying P itself. Okay, P and Q and R are all Boolean variables here. They all take on a truth value, either true or false. So if I say P and P, that's equivalent to just saying P. Same thing with P or P. Okay, if I say one of these two has to be true, then P itself has to be true. On the and, if I say they're both true, well, they're both P, so P itself is true. Okay. The commutative laws, I hope, are very intuitive. The and statement, it doesn't matter if you say P and Q or Q and P. They both have to be true for the statement to be true. Same thing with or, it's commutative. P or Q is the same as Q or P. All right. There's a couple of little bit trickier ones here. The absorption rules, for example. When I say P or both P and Q, then that's equivalent to P. It can be reduced to P. If you don't care about what Q is, you can reduce this to P, because it's saying that either P is true or both P and Q are true. And in either case, P is true. Same thing with this one over here. If you say P and, actually P and anything can be reduced to P if you want it, if that's what you want to conclude. So P and either P or Q can be reduced to P. Those are called absorption. You don't have to remember the names of these rules, but you should be able to use them. Okay? You know, associative, distributive, double negative, De Morgan's, commutative, you have to remember those. Idempotent and absorption and bound and negation rules, I don't really remember them by those names myself. Anyway, those are the absorption rules. The bound rules are if I say that both P and something which is false, that's always going to be false, because they're both it's never going to be the case that both P and something which is false are going to be true. So that whole statement is always false. P and something which is always true reduces to P, because if P is false, if P is a 0, then I have 0 and 1, which is false, which is equal to P in the first place. And if P is true, then I have 1 and 1, which is also true, and which is also equal to P. You can go through the same thing here. P or 1 is always true, because it only takes the 1 to make the statement on the left true. And P or 0 is equal to P. If P is 0, then I have 0 or 0, and that's false. If P is 1, I have 1 or 0, which is true. In either case, it's equal. You can make truth tables to prove these guys if you don't believe it by just looking at it and thinking about it for a minute. Finally, the negation rules, P and not P is always false. You can never have a Boolean variable which is both 0 and 1. Okay? Similarly, if you say P or not P, well, one of those is always going to be true. If P is true itself, it's the first one. If P is false, then the second one becomes true. And on an or statement, you only need one of the two to be true, so that's always going to be true. And you should be able to use these in your working of the logic when you do some algebra with these forms. And so I'll show a couple examples of that here on this page. The first one I'm going to do is going to be very similar to problem 9 on your homework. It's going to be to simplify, using algebraic rules of logic, simplify the statement not P and Q. Okay? And basically what I'm going to do is I'm going to recognize a De Morgan's type of form here where I've negated an AND statement. And when I negate an AND statement, I can bring the minus sign in, and I get a double negative on the P, so I'm not even going to write the double negative, I'm just going to write P. It switches an AND to an OR, and it puts a negative on the Q. Okay? And this is in fact a simplification because there's fewer negative signs. Okay? And if you were to interpret both of these as English statements, the one on the left would be kind of confusing because you'd have these sort of double negatives within the statement. And if you've ever made a statement with double negatives in it, you know you can usually simplify it to a statement that doesn't have double negatives if you think about it. So there's one example, almost just like one of your homeworks. Let's see. Another one that we can simplify is something like this. Let's say P and not Q, or P and Q. Okay, and I'm going to recognize this one. We want to simplify this. So I'm going to recognize this one as a distributive law. So this is a P and operating on two other things. Okay, so I'm going to write that this is equal to P and then I'm going to put those two other things here, not Q or Q. Okay, and now we know from the previous page that Q or not Q, where is it? Q or not Q is always true. So I'm going to write that this is equal to P and 1. And now I'm going to simplify this further to be just P. Because if P is true, then I have a 1 and 1 and it's true, which is equal to P itself. And if P is false, I have a 0 and a 1, which is false, which is equal to P itself too. So this one really simplified down. Okay. The other one I'm going to do for you is to show you how to use rules of logic to simplify the following statement. I'm going to write it out here. R and P or Q or not P or R. Okay. Is this what I want here? Hold on, let me make sure I've got my... Yeah, this is what I want. First of all, I'm going to notice that I've got these OR statements here. Now, normally, you don't need to put parentheses when you have multiple OR statements. But in this case, because we have the OR statement in these parentheses already here, let me get my arrow. This OR statement's in these parentheses already, so I can't just take these parentheses off. But what I do, the very first thing I notice is that I've got sort of a De Morgan's sort of situation here. So I'm going to apply De Morgan's first. I'm going to copy this down as R and P or Q or, and now I'm going to turn this into P and not R. And I applied De Morgan's there. I take the minus sign on the inside and I turn the OR into an AND. When I take the minus sign on the inside, I get a double negative on the P, which I just write as P, and I negate the R. Okay? And now, what I'm seeing here, it's a little bit tricky, but what I'm seeing here is I see three things OR'd together, and so it doesn't matter what order they are. And I also see that I have a P and on two of them. I have a P and here and a P and here. And a P and here. And I'm going to factor out that P and I'm going to write this as P and R or P and not R, or Q. And now I've rearranged things a little bit. I rearranged on the inside of the and I rearranged all three terms in the or, and now I see a distributive law that I can do. I can factor out this P, and I can have an R or a not R. And then that whole thing, or Q. I'm going to put parentheses just to be safe here. And then R or not R is always true. So this is P and true. There's a 1. Or Q. And P and 1 reduces to P. So the whole thing reduces to P or Q. Okay, and I'm going to double check that now. I've got R and P or Q. I've done my De Morgan's correctly here, turned the or into an and negated both of them. And now I've rearranged this one. I've rearranged the Q or P and not R, P and R or not R. And R or not R is 1 because one of them's true. P and 1 is P. Yeah, this works. Okay, so that's it.